So this is the video for Lab 6. This week's lab, we're going to look at a big snowstorm that affected our region, mainly north of here, back in 2015. And you can check this report on this case from the Chicago Weather Service office if you want to get more information about this. The data are available through the Scholar computing system. So if you load up this in your URL in a browser, you can log into that system with your career account. And follow the instructions to get access to the files that we're going to use, and the main instructions will show up in this different font here. Things you need to type into terminal in order to do the tasks for the lab. So for this lab, we're going to start looking at the quasi-geostrophic equations and the simpler version of the equations of motion that we can use if we assume we're dealing with sort of large-scale weather systems, synoptic scale flow. And we'll talk about the difference between the vorticity equation if we make these assumptions, and how it simplifies that equation to basically this form, where we can come up with an expression for how the vorticity changes with time, and that being equal to the vorticity advection and what we call the stretching term. Well, if we use this equation, we can understand why the vorticity is changing with time. So that's definitely an important aspect to this. But we can also estimate these terms. So look at how the vorticity has changed with time. Look at the vorticity advection, and solve for the divergence. Basically rearrange this equation so we can estimate the horizontal divergence. And there's a nice, I guess I'll call it a trick, that we can use to estimate this local rate of change that is called the frozen wave hypothesis. And this frozen wave hypothesis is what people use to analyze weather systems and determine the wind flow relative to the weather system. So it's a different perspective. You're looking at the winds, how they would flow from the perspective of the weather system as it moves. So we call that system relative flow. And this type of analysis is widely used to try to, it makes it easier to identify different airstreams relative to a cyclone. And things like the warm conveyor belt, the cold conveyor belt, the dry intrusion are easiest to find when you use this system relative flow approach. So the frozen wave hypothesis basically is a way to estimate the local time derivative, and it ends up being equal to sort of an imaginary advection by the system motion itself. So this c sub x and c sub y are components of the system motion vector, capital C. And if we substitute that back into our equation, we can rearrange it and basically come up with an equation for the horizontal divergence, which I usually call lowercase delta, the Greek letter delta. And it just becomes the advection by the system relative flow multiplied by -1 in the numerator, and the denominator is just the Coriolis parameter, also multiplied by -1. And so if we cancel those minus signs, we get this expression that the divergence is equal to the advection, basically the vorticity advection by the system relative wind divided by the Coriolis parameter. And these are things that we can use the software to calculate and actually come up with numerical values for the horizontal divergence. It's also good to see this relationship, really, that the divergence is basically directly related to the vorticity advection. So if we're looking at the vorticity advection and that happens to be positive, we should expect there to be divergence in that area. And if the vorticity advection is negative, we should expect there to be convergence. If the divergence is less than 0, we call that convergence. So that's really the point of this lab, is for you to see this relationship between the divergence and the vorticity advection. So the lab basically goes through this one particular time in this storm, asks you to basically go through this process. So in order to figure out the system relative flow, you need to track some aspect of the storm and determine the system motion vector. And there would be questions for each part of this lab that I'm asking you to answer. And you can fill these answers in on the worksheet, which is a separate doc, and basically just type your answers in. For most of these, there's either very simple calculations that need to be done, or just reading numbers off the map. But take careful note of the units as you do this, and make sure you provide the units that are appropriate, and make sure that they cancel out when you do calculations. So the worksheet basically are the questions you need to answer, and the lab sort of steps you through the different parts of this system relative flow analysis and calculation. So let's take a little bit closer look at this to try to illustrate what we're talking about here with this frozen wave hypothesis and the quasi-geostrophic vorticity equation. So the idea for this frozen wave hypothesis is that weather systems move around, and if we assume that the shape of the weather system, the amplitude, doesn't change with time, basically it's a frozen wave, but it does move, then we can use that to come up with a simple approximation to local time derivatives, basically how things change with time. Okay, so here I've got this imaginary surface flow, so we've got sea level pressure contours here, and isotherms, dashed lines, and let's say that this system doesn't change its shape at all, but it just moves from west to east at 20 knots. So we could track this. We could take a look at the location of the surface low at one time, see the location at a later time, look at the difference between those, and divide that over the time difference, in this case 6 hours, to come up with a system motion vector, C. And if we were to report that like a wind, we would say the motion is from 270 degrees at 20 knots. Okay, so if it moved 120 nautical miles in 6 hours, then its speed would be 20 knots. And since it's just going directly from west to east, its direction is 270 degrees. Okay, so the shape, the amplitude of this system didn't change with time, it just moved. Well, let's say we're interested, say this is Lafayette, this little plus sign. We're interested in estimating the local time derivative of temperature at Lafayette. So this would be like partial derivative of temperature over time. So we could look on the map, sort of interpolate between these two isotherms and say that it's 17 degrees C at this time, and then 6 hours later it looks like we're pretty close to the 5 degrees C isotherm, so we'll say it's 5 degrees 6 hours later, and we can subtract those, divide by the time difference, do a finite difference approximation to the partial derivative, basically the local rate of change of temperature. And it dropped 12 degrees in 6 hours, so dt in this case is -2 degrees per hour. So that's definitely one way to determine this time derivative, but we can use this frozen wave hypothesis to estimate the time derivative as sort of an imaginary advection, where the advection is being done by the system motion. So if we were to calculate the temperature advection by the system motion vector, which would be minus c dot del t, we would get the exact same value, -2 degrees per hour. And so, just estimating the temperature advection where we figure out the gradient in the direction of the wind. In this case, it's the system motion is the wind that we're using to do the advection. The difference in temperature between these 2 points is 17 minus 5 degrees. The distance, the delta x, would be 120 nautical miles. And we multiply that by the wind speed, in this case the system motion speed, 20 knots. And sure enough, that we get the exact same value, -2 degrees per hour. So the idea is to use this pretend advection by the system motion in place of the local time derivative in places where we need to do this for calculations. And that's usually helping us to estimate the total derivative. Okay, so let's say we're looking at the total derivative of pressure. And these are the terms. So the local pressure derivative, dPdt, and then we have horizontal advection terms, U dpdx, V dpdy, and vertical advection, W dpdz. So let's ignore the vertical advection. Let's just assume it's close to 0, just for to simplify this, and use the frozen wave hypothesis to replace this partial derivative with this other advection by the system motion. So that's minus c sub x dp dx minus c sub y dp dy, where these c sub x and c sub y are the horizontal components, east-west and north-south, of the system motion. And we can combine these two together, right? We can substitute in this equation, and notice that we have terms, two terms that have dp dx that we can combine together, and two terms with dp dy that we can combine together. And basically approximate the total derivative as this modified advection, where we're doing the advection by the system relative flow, basically V minus C, where V is the wind, right? It has U and V components, and then C is the system motion vector, which has CX and CY components. And I mean, this is advection times -1. When we think of advection, it's usually minus U dp dx minus V dp dy. So we're really multiplying that by -1 here to approximate the total derivative. Okay, so when we calculate advection, when we think of advection, when we use the Nmap2 to come up with numerical values of advection, we're really looking at minus V dot del P in this case. And so we have to multiply that again by -1 to get this value. The nice thing is that we can get the computer to do this for us. We can take the wind vectors, we can take the whole wind velocity field, we can subtract off a system motion vector, you know, really everywhere, and come up with this system relative flow. And that helps us visualize what the flow field would be if we were to follow the system around. And this is really what the weather system notices, the advection that occurs, as well as the changes due to the system motion as that weather system moves around. So this vector subtraction can fairly easily be done in the program. All we have to do is come up with a system motion vector. We have to track some system, see how it's moving, and come up with a speed and a direction, turn that into east-west, north-south components, and plug that in so the computer can do this V minus C for us. Now, I mentioned before we're going to be looking at the quasi-geostrophic vorticity equation, and we usually call the quasi-geostrophic system of equations the QG equations for short. And these are simpler versions of the full equations of motion, where we can neglect terms that are relatively small for large-scale flow, what we call synoptic scale flow. Wavelengths that are thousands of kilometers, typical wind speeds, order magnitude of 10 meters per second. Basically the sort of the ridges and troughs that we see in upper level maps, surface cyclones, anticyclones, the large-scale weather systems that we typically track when we do day-to-day weather forecasting. Now, if we do scale analysis, this is what we would do in dynamics and try to come up with a dimensionless number that we can factor all the terms. We would see that we could come up with a Rossby number, which is basically the ratio of the acceleration to the Coriolis force. And for this type of flow, we would find a fairly low Rossby number, around 0.1. So basically what that's saying is we have weak acceleration, but it's not zero. So if the acceleration was zero, then the flow would be purely geostrophic. But since we are allowing some acceleration, it's not quite geostrophic. It's almost geostrophic. And that was called quasi-geostrophic in the literature, and that's what we call this. Now, if we were dealing with accelerations that are larger, they're basically the same order of the Coriolis force, then we can't make these approximations. It's a different type of flow, and that would be more mesoscale, smaller scale waves, and these equations wouldn't be applicable to that type of problem. So if we make this approximation, it changes the vorticity equation. So the full vorticity equation is shown in the first line. So we're looking at zeta plus f. We're looking at absolute vorticity, how it changes with time. There's horizontal advection. So notice that it's minus u d by dx minus v d by dy. This is how we think of advection. There's vertical advection, minus omega d by dp of zeta plus f. There's the stretching term. So the delta is the horizontal divergence, and that's acting on the existing vorticity. And so this is like the ice skater. As they bring their arms in, they spin faster. So that's the effect of convergence and divergence on the vorticity, to either spin it up or spin it down. And then there's the tilting term. These two terms that involve the interaction between vertical shear and a horizontal gradient in vertical velocity actually tilt the horizontal vorticity into the vertical. Okay, so vorticity equation is basically advection, stretching, and tilting. Well, the quasi-geostrophic version of this is very similar. Okay, instead of zeta plus f, we're looking at zeta sub g plus f. So we're assuming the vorticity can be described as the geostrophic vorticity. So we're looking at the curl of the geostrophic wind here, zeta g. And that is true. That's been replaced in the advection terms as well. Notice that the advection is by the geostrophic wind also. So the horizontal advection is the horizontal advection of the geostrophic vorticity by the geostrophic wind. So that's a simplification of the horizontal advection in the full vorticity equation. Notice there's no vertical advection, so we're neglecting vertical advection of vorticity. Notice there's no tilting, so we're neglecting tilting. And the stretching term has been simplified. The stretching is only acting on the Earth's vorticity. Basically, the Coriolis parameter gives us the vorticity that's due to the Earth's rotation. So we're neglecting the stretching of the relative vorticity in the stretching term. So this is the equation we're going to use, the QG vorticity equation. And we want to use this to estimate the horizontal divergence, the delta term here. So if we rearrange that equation and solve for delta and use the frozen wave hypothesis to estimate the time derivative, we get this equation, that the divergence is equal to the geostrophic vorticity advection by the system relative geostrophic wind divided by F. And that's what we're going to solve for in the lab. Basically go through the steps of determining these values, finding the system relative flow, modifying the code, calculate the advection of the geostrophic vorticity by that system relative wind, dividing it by F, and then comparing the value that we estimate to the value that the model actually predicted, and see how good or bad this approximation happens to be. So that's all that I have for this lab. Let me know if you have any questions, and good luck.